Students, in the last class, we have discussed about rings, fields, integral domains, and prime ideals. Okay, what is a prime ideal? An ideal S is said to be a prime ideal if for every A comma B belongs to S, for A comma B belongs to the ring R, AB belongs to S implies either A belongs to S or B belongs to S. In such a case, we call the ideal as a prime ideal. Okay. See, suppose we say, let us call a non-empty set S of R of a ring R is said to be multiplicatively closed. Multiplicatively closed if A belongs to S, B belongs to S, implies AB belongs to S. We say that generally if it satisfies closure property with respect to multiplication, then we say that the set S is multiplicatively closed. Okay. Students, in all of you got material in 2.5.
Yes, ma'am.
Yeah. I will give the proofs of very important theorems. All the theorems proof are given in your material. From that, you can learn the theorem. See, take total, you have 18 units. Out of 18 units, if you prepare 9 units perfectly, then you can definitely, you can pass and you can get good marks also. In that, I'll give you very important theorems. From that, you prepare. Okay. Now, see, next first theorem is on this theorem is let P be an ideal of a ring R. Let P be an ideal of a ring R. Then P is a prime if and only if there exists a multiplicatively closed set. There exists a multiplicatively closed set S in R, which is this is 2.5, unit is 2.5. In unit 2, this is 2.5, prime ideals and nil radicals. Prime ideals and nil radicals.
Okay.
Yeah. Okay, prime ideals and nil radicals. In this, the first theorem is important. Let P be an ideal of ring R. P is a prime. Okay, and then P is a prime means prime ideal. Okay, and P is a prime ideal if and only if there exists a multiplicatively closed set S in R such that or P is maximal, which is maximal among the ideals. Among the ideals which are disjoint from S. What do you mean by a set is disjoint? Two sets are disjoint. Two sets are disjoint if they have no element in common. So if and only if condition means we have to prove the theorem in two parts. Prove the theorem in two parts. First, suppose P is a prime ideal. First, suppose P is a prime ideal. I told you, you have to concentrate on two things. What is given, what you have to prove. Then you will get definitely how to prove. Given that P is a prime ideal. So what do you mean by prime ideal? AB belongs to P. If capital P is a prime ideal, AB belongs to P implies either A belongs to P or B belongs to P. What you have to prove? We have to prove that there exists a multiplicatively closed set S in R. The next point we'll discuss later. We have to prove that there exists a non-empty set S which is multiplicatively closed. What do you mean by multiplicatively closed set? You have to prove that A comma B belongs to S implies AB belongs to F. So first proof. Suppose P is a prime ideal. Okay. Now we prove that there exists a multiplicatively closed set S in R. Okay. So P is prime ideal. We prove that there exists a multiplicatively closed set in R and any ideal disjoint from S must be contained in P. For that, what we will do? We take S equal to R minus P. Suppose if you take S equal to R by R minus P, or we can say that we can take R by P, and there are R minus P contains elements which are in R but not in P. So suppose if you take S means definitely your S will satisfy because ring and prime ideal. What do you mean by prime ideal? Prime ideal means AB belongs to P implies, sorry, A into B. A into B belongs to P implies either A belongs to P or B belongs to P. That means you have C. That means you have A comma B belongs to S implies, what do you mean, Andy? A comma B belongs to R minus P. That means both are C. A comma B belongs to R, but A comma B does not belongs to P. But you have A comma B belongs to R implies AB belongs to R and AB belongs to R. But A does not, ante ikkada A comma B does not belongs to P ante AB also does not belongs to P. That means you have AB belongs to R minus P. That means you have S is a multiplicatively closed set. S is a multiplicatively closed set. So whenever P is an ideal, we have proved that it is a multiplicatively closed set. Now conversely, suppose students, is this clear to you? First, what I supposed? Suppose P is any prime ideal. Then what you have to prove? There exists a multiplicatively closed set in R. And any ideal disjoint from S must be contained in P. For that, what I have taken? I took S equal to R minus P. What do you mean by R minus P? My S contains elements of R which does not belong to P. S does not belong to P. So suppose you take A comma B belongs to S, then A comma B belongs to R minus P. That is A comma B belongs to R and A comma B does not belong to P. Since P is a prime ideal, AB does not belong to P. So you have AB belongs to R, AB does not belong to P means AB belongs to R minus P. So S is a multiplicatively closed set. Now, conversely, suppose S is any multiplicatively closed set in R and P is maximal among all the ideals of R which are disjoint from S. That is, you have P intersection S is empty. That and if I is any ideal, if I is any ideal, if I is any ideal of R, then definitely you will have I intersection Students, is my screen is visible?
Yes,
Hello?
madam. Yes, madam.
Okay, all of a sudden board has disappeared because of network connection. 1 minute.
Your voice is stuck, madam.
Yeah. That's what I'm changing to another network. Suppose if I is any ideal, then I intersection S is also empty set. So then what we have to prove? We prove that P is a prime ideal. Okay. Now that is what do you mean by this? This means if P is the subset of I told you, no, it is one of the maximal ideal. That means if P is the subset of I implies P equal to I. This is what you mean by P is maximal among all the ideals of R which are disjoint from S. That means there is no ideal between P and I. P and S, and if P is a subset of S is subset of I, then you definitely you will have P equal to I. Just internet connection is getting unstable. 1-2 minutes more. Okay. First, we prove that P is a proper ideal. Otherwise, what you have to do? Then you may have S may be empty set. So that is the reason you have to prove that P is a prime ideal. Suppose you have to consider one minute. Students again. Students, sorry for the inconvenience. Screen sharing is not coming. Host disabled అని వస్తుంది. Students, is my voice is clear? Students? Okay, actually, this host disabled participants screen sharing అని వస్తుంది. Just I will check out with them 1 minute. Students, is the screen visible? Okay. Okay. Students, this is the one I am explaining. Let P be an ideal of ring R, then P is a prime ideal if and only if there is a multiplicative closed set S in R such that P is maximal. P is maximal. P is maximal among the ideals which are disjoint from S. This is what you have to prove. This is one important theorem. Suppose P is a prime ideal, put S equal to R minus P. Then S is a multiplicatively closed set in R, and any ideal which is distinct from S must be contained in P, because S is the big set and that is P is the maximal ideal. So conversely, suppose S is any multiplicatively closed set in R and P is maximal among all the ideals of R which are disjoint from S. That is, you have P intersection S is empty set, and for any ideal I of R, I intersection S is also empty. Why? Because P is a subset of I means P is equal to I, because P is a maximal among all the ideals. Now we have to prove that P is prime. To prove that P is prime, we observe that P is a proper ideal and otherwise you may get SAB empty set. Now we prove that to prove P is prime ideal, we prove that A comma B belongs to R and A and B does not belongs to P. See here, we say that P is a prime ideal if A comma B belongs to, A into B belongs to P, implies either A belongs to P or B belongs to P. Suppose if A does not belongs to P, B does not belongs to P, AB also does not belongs to P. So consider two elements A and B such that A does not belongs to P and B does not belongs to P. Now put I is equal to P plus RA and J equal to P plus RB, because we know that the sum of two ideals is again ideal. Okay, here P is a subset of I and P is a subset of J. And A and B belongs to, A belongs to I and B belongs to J. Now, by maximality of P, I and J, these are not disjoint with S and D. That is, you have I intersection S is empty, J intersection S is empty. Now choose X belongs to I intersection S and Y belongs to J intersection S. So you tell me, Emma, what is the form of element X? X is, tell me, P1 plus R1A. And other element is, you have X is P2 plus R2B. Okay, you are saying that X and Y belongs to S means you have X is of the form P1 plus R1A and Y is of the form P2 plus R2B. So you have, now you have X and Y belongs to S, isn't it or not? You have X and Y belongs to S. Now consider X, Y, take the multiple. You will get P1 into P2 plus R2B plus again R1A into P2 plus R2B. You multiply all these elements, okay, and or elements of S, because we are supposed that S is multiplicatively closed set. So you have XY belongs to S. If you have XY belongs to S means you have AB also belongs to P. AB belongs to P. You have XY belongs to S and AB belongs to P means, XY belongs to S intersection P. XY belongs to S intersection P. That means you have XY belongs to S is correct. If you take XY belongs to P, okay, and if AB is in P, see here, if AB is in P, then XY also belongs to P. That is, XY belongs to S intersection P. So this is contradiction. Therefore,
Madam, screen mode is not.
My screen is not visible?
No, ma'am.
That is, you have AB does not belongs to P. So this proves that P is prime ideal of R. 1 minute. They said, okay, 1 minute. Why it is not coming? So how to do, how to go about this problems? 1 minute. Students, sorry for the inconvenience. Is my voice is clear? Hello? Students?
Yes, madam.
Yeah. Okay.
Yes, madam.
Students, previously what I have explained is the first important theorem. Here, an ideal P of a ring R is said to be a prime if P not equal to R and any A comma B belongs to R, AB belongs to P implies either A belongs to P or B belongs to P. And I explained about what do you mean by multiplicatively closed. If for every A belongs to S, B belongs to S implies AB belongs to S, then we say that the set is multiplicatively closed. So, okay. So if P is an ideal P of R is prime if and only if it's a complement R minus P and okay, and if and only if R minus P is multiplicatively closed. That you have to make a note of it. This is what I explained and I have written on the board also. See here, suppose P is a prime ideal. See here. Suppose P is a prime ideal. What is we have to prove? We prove that there exists a multiplicatively closed set in R and any ideal disjoint from S must be contained in P. For this, let S equal to R minus P and R minus P and it is R complement. Okay, for P complement. So here, if S is equal to R minus P means now what is P? P is prime ideal. P is a prime ideal. So R minus P is our required thing. So here we prove that S is a multiplicatively closed set. Now take A comma B belongs to S. That means you have A comma B belongs to R minus P. So you have AB belongs to R and AB does not belong to P. Hence, you have S is a multiplicatively closed set. Now, conversely, suppose S is any multiplicatively closed set in R. Multiplicatively closed set in R and P is maximal among all those ideals of R which are disjoint from S. That means you have P intersection S is empty set. Disjoint means they have no elements in common. They have no common elements. And what do you mean by this? P is maximal among all those ideals of R which are disjoint from S. You have P intersection S is empty. And if I is any ideal, you have I intersection S is also empty. Because P is maximal among all these ideals, if P is a subset of I, because I is any ideal, so if P is a subset of I means you must have P equal to I. Okay. Now what is required to prove? We prove that P is prime. If P is prime means you take two elements A and B in P. We prove that if either A belongs to P or B belongs to P or A belongs to P, B belongs to P implies AB belongs to P. So we are proving it by contradiction. Students, am I clear? In order to prove P is a prime ideal, we prove that AB belongs to P implies either A belongs to P or B belongs to P. For this, for my convenience, I am supposing that A does not belong to P and B does not belong to P. Then what I will prove? I will prove AB also does not belong to P. For this, what you will take? Yesterday I gave one example. RA is an ideal. Capital RA is an ideal. RB is also an ideal. Do you remember, students? RA. What is RA? RA is the set of all RA such that R belongs to R. Whenever R is a commutative ring, it is an ideal of R. So what we will prove now, you take ideal I as P plus RA, ideal J as P plus RB. Now P is a subset of I and J and D. Otherwise, what you will have, A belongs to I, B belongs to J kada. Yeah. A belongs to I, B belongs to J. So therefore, you have P is a subset of I and P is a subset of J. And by maximality of P, what I am saying here, what do you mean by maximality? It is not P is maximal and any ideal is contained in P. P is not contained in other ideals. So that is the reason I and J are not disjoint with S, because P is not disjoint with S. I and J also not disjoint with S. Okay. So you take two elements, X comma, X belongs to I intersection S and Y belongs to J intersection S. Along time my elements, then X is of the form P1. So what is I and A? I is P plus RA. So element will be of the form P1 plus R1A. In J, elements will be of the form P2 plus R2B, where P1 and P2 belongs to P, A and B. A belongs to I and B belongs to J. So what is our assumption on S? S is multiplicatively closed set. Therefore, you have definitely XY is in S. You have XY is in S. Ante entandi, you have P1, P2 plus P1 R2B plus R1A P2. All these elements and R1, R2, AB. All these are elements of S. That means you have AB is also element of S and AB is element of S and AB, if at all, if AB belongs to P, then you have XY also belongs to S intersection P. Why? Because always XY belongs to S and if AB belongs to P, this XY is also in P. So you have S intersection P contains a common element XY, but our assumption is P is disjoint with S. That means S and P have no elements in common. Therefore, A does not belong to P, B does not belong to P, implies AB does not belong to P, which proves that P is prime ideal of R. Students, this is one important theorem. Any doubts you can ask. Hello?
No, ma'am.
Got the point? Okay. So this you prepare. Next one. Next definitions. See here. This is saturated, non-saturated, all this is not that required. Next one is, see, next theorem on prime ideals is very important one. 2.5.10. See, let P and Q be distinct prime ideals of a ring R and P is a subset of Q. Immediately, whenever in the statement you see prime ideal means, oh, AB belongs to P means either A belongs to P or B belongs to P. XY belongs to Q means either X belongs to Q or Y belongs to Q. So, you have, let P and Q be distinct prime ideals of a ring R and P is a subset of Q. Then there exists distinct prime ideals P1 and Q1 such that P is a subset of P1, P1 is a subset of Q1, which is a subset of Q. And there is no prime ideal between P1 and Q1. Okay, if you see the previous year question papers, this is one important theorem. Okay, I will explain all important 10 marks and 5 marks theorems. Okay, this is for 10 marks. Now, what we are going to prove, if there exists two distinct prime ideals between any two prime ideals. Ante basically you can always insert ideals between ideals, and that means like this itla. Okay, this if suppose this is R. Okay, you have this is P ankondi. This is P1. P1 is big kada. P1 is this Q1, sorry. P1 is contained in Q1. Q1 is contained in Q. Like this, always you can have hierarchical structure of a ring. Okay. Whenever you want to learn a theorem, you read the statement only for more than 2 to 3 times. What it is conveying to say. Our aim is to prove between any two distinct prime ideals of a ring R. Here R is a commutative ring. R is a commutative ring. Between any two distinct ideals of a ring R, there exists two distinct prime ideals, P1 and Q1, such that P is a subset of P1 is properly contained in Q1 is a subset of Q. Generally, that means these are all spaced. These are all spaced. There is no ideal between P1 and Q1. So you have P is a subset of Q and P is subset of Q. Is this diagram correct? Just let me draw once again. See, you have Q. Correct only I have drawn. This is Q. This is P. So here you will have P. P1 is the big one. Okay. P is a subset of P1. And P1 is contained in P2. Like that, you can always construct two prime ideals between any two distinct prime ideals. So how you prove? Let S be the class of all chains of prime ideals between P and Q. And P is the set of all I such that I is a prime ideal and I lies between P and Q. Then S is called the class of all chains in P. All of you know what is a chain? A set B is said to be a chain. If you take A comma B belongs to B means you have either A is less than B or B is less than or equal to A. That means any two elements are comparable. One is contained in other. Then we say that it is a chain. Now, see, if Ci, just go through this. If Ci such that I belongs to delta is a chain in S, that is each Ci is a chain in P, and for any I comma j belongs to delta, you have either Ci is a subset of Cj, Cj is a subset of Ci. This is what you mean by a chain, and union is also a chain, and union of sets C1, C2, etc. Cn is also a chain in P. So whenever it is a chain in P, it is also a chain in S and D. So what you are taking, S is the class of all chains between the ideals P and Q. Okay, you are taking like this. P untundi, Q untundi. P is a subset of C1, subset of C2, subset of C3, and so on. Like that we are taking. So what do you mean by, anybody knows what is John's lemma? John's lemma says that, okay, by applying John's lemma, you have S possesses a maximal member. The set of all class of prime ideals will have a maximal member. So this is a chain of prime ideals between P and Q. That means you have, for any prime ideal I, you have P is a subset of I is a subset of Q, and I is not in C and D. But C union I is not a chain. And C union P comma Q is a chain in P. Now choose an element A belongs to Q such that A does not belong to P. Why? Because it is a chain, means any two elements are comparable. That is, you have either P is the subset of Q or Q is the subset of P. So P is properly contained in Q means there is an element which is in C. Here P is the subset of Q means every element of P is also an element of Q. There are some elements in P which are not in Q. So A does not belong to P is possible. So you take two sets C1 and C2. You partition C into two sets C1 and C2. C1 is I, set of all I such that I belongs to C, A does not belong to I. C2 is the set of all J belongs to C, but A belongs to J. Then from these two, what are the characteristics of these C1 and C2? Your C is C1 union is C2, and these two are disjoint sets. And P belongs to C1 and Q belongs to C2. Also, for any I belongs to C1 and J belongs to C2, J is not subset of I and D. So, and you have, since C is a chain and J is not a subset of I, means you must have I is a subset of J. So you take P1 is the union of C1 and Q1 is intersection of J belongs to C such that A belongs to capital J. This is intersection of C2. This is union of C1. Then 100% you will have P1 is a subset of Q1 and P is a subset of P1 is a subset of Q1, subset of Q. Okay. And also every member of C1 is contained in P1 and that every member of C2 contains Q1. So there is no member of C. There is no member of C is properly between P1 and Q1, and C is the maximal chain. There is no prime ideal properly between P1 and Q1. So this is about the theorem. Students, once you go through this theorem, just for 5 minutes, whether you understand or not. What do you mean by chain, Andy? What do you mean by chain? Chain means, suppose A comma B belongs to, we say that a set S is a chain. A comma B belongs to S implies A less than or equal to B or B less than or equal to A. That means you have any two elements are comparable. If A is less than or equal to B, then definitely B is not less than or equal to A. So chain means it will be like this. Chain of sets means A1 is the subset of A2 is the subset of A3, like that. What the John's lemma says, see here, like this. One is contained in other one is contained in other, like that. So at the most you have, finally you have a maximal element. That maximal set only we are taking it as C. Students, once just read, this is for 5 marks and this result is useful for coming chapters. Take one pen and the pencil and paper, try to understand the concept. Here you have R is a ring. R is a ring. Okay. Here P is subset of Q. Whiteboard में देता हूँ. Sorry. You have P is subset of Q. P is subset of Q. then you can find P1. This is P1 and this is Q1. What he says, always you can find a pair of two ideals between P and Q. This is what he says. Okay, ma? How I am proving? I am considering chain of all prime ideals between P and Q1. Between P and Q, I am considering all chains of prime ideals. How I am that is, how I am taking capital P and D. P is an ideal set of all I, such that I is a prime ideal and P is a subset of I is a subset of Q. And I is variable anamata. You can find n number of ideals between P and Q. This is called chain. And chain means, suppose you are saying that Ci, I belongs to delta is a chain. Then you have either Ci is a subset of Cj or Cj is a subset of C1. Suppose if you take union of all elements in a chain, that is also once again chain. So it is a chain in P and it is a chain in S also. So you have S contains a maximum member, say C. And this maximum member C, I am dividing into two sets, C1 and C2. So P1, you consider it as a union of all C1. Q, consider it as a union of C2. Then definitely you will get P1 is a subset of Q1. And hence you have P is a subset of P1 subset of Q1, which is the subset of Q. Any doubt, students?
No, ma'am.
Okay. So this is one important one.
Which unit, ma'am?
This is second unit.
Okay,
And
thank you.
yeah, next one is annihilator. What do you mean by annihilator? I think in group theory we have learned annihilator, the set of all x belongs to R such that Ax equal to 0. This is known as annihilator of R, ring R. Annihilator is always annihilator ideal. It becomes ideal also. Okay. Next, this is for 5 marks. Let P be let P be an ideal of a ring R such that P is a maximal member of a class of all annihilator ideals of non-zero elements of R. Then P is a prime ideal. Students, my request is this commutative algebra, when compared to other subjects, this requires more what you call concepts in ring theory, fields, and concept oriented. So that is the reason what I am planning to do is I will focus on important questions only. I'll explain the definitions and theorems. Is that okay for you? Hello?
Yes, ma'am. Okay, ma'am.
Okay, ma'am.
Yeah. Like that, we'll perfectly you prepare for 9 units. 9 units, half of the syllabus, if you prepare means definitely you will get full marks. And after that, I'll give you the important theorems. Now, let S equal to annihilator of non-zero element. So, given that P is a maximal member in S, that is, P is maximal member and B not equal to 0, 1 does not belong to P, means P is a proper ideal of R. Yesterday, I told you, if 1 belongs to the ideal A, then there is no difference between A and R. So here also P is not equal to R, and if P not equal to R means you have 1 does not belongs to P. If 1 belongs to P means definitely P will become R. Okay. So we prove that P is a prime ideal. If you want to prove P is a prime ideal, consider XY belongs to P. XY belongs to P means what is P? P is annihilator of all non-zero elements. What do you mean by annihilator? Xy belongs to P means B into Xy is 0. Okay, ma? So if X does not belongs to P, then you have Bx not equal to 0. And you have P is contained in annihilator of P. That is nothing but annihilator of Bx, which is not equal to 0. Therefore, annihilator of Bx is P, which implies that Y belongs to P. So you have whenever Xy belongs to P and X does not belongs to P, we have Y belongs to P. So you have P is a prime ideal of R. Okay, this is 5 marks question. What it says, if P is an ideal of ring R and it is a maximal member of class of all annihilators. What do you mean by annihilator? Annihilator means annihilator of A means the set of all X such that Ax equal to 0. Okay, annihilator is an ideal and annihilator is an ideal of a ring R. Okay, so maximum member of annihilator is a prime ideal.
Prime ideal.
Yeah. Next, see here, we define, see, an ideal I of a ring R is finitely generated. This is the notation for finitely generated. When we say that it is finitely generated, every element of I is the linear combination and the R1x1 plus R2x2 plus and so on plus Rnxn. Then we say that it is finitely generated. Okay, ma? Finitely generated means, see here, an ideal I of a ring R is said to be finitely generated if X equal to x1, x2, etc., xn, then every element, suppose if I take alpha belongs to I can write alpha is equal to R1x1 plus R2x2, so on, plus Rn xn. Like linear span in the vector space, you have to write, if alpha is in I, then alpha can be written as alpha 1 x1, R1 x1 plus R2 x2, so on, Rn xn, where R1, R2, etc. belongs to xn. Okay, Andy?
Okay, ma'am.
Ma'am, page number
31, Amma. Page number 31. Okay?
Okay, ma'am. Thank you.
Yeah, no, I'm continuing. One more theorem I'll tell you. Okay?
Okay, ma'am.
When come, see, let P be an ideal of a ring R. Suppose P is not finitely generated. Okay, P is not finitely generated and is maximal among ideals of R that are not finitely generated, then P is a prime. More than this you can leave it off. Next theorem is very important. This theorem. Why I am reading these statements? Just read the statements. Suppose if ideal, P is an ideal of a ring R, and if P is not finitely generated, and it is maximal among all the ideals of R which are not finitely generated, then P is a prime. But here, let R be a ring in which every prime ideal is finitely generated. It's a very, very important theorem. Is my screen is visible? Hello?
Yes, ma'am, visible.
Yeah. Let R be a ring in which every prime ideal is finitely generated. Then every ideal of R is also finitely generated. What do you mean by prime ideal is finitely generated? If P is finitely generated means alpha belongs to P can be written as alpha equal to R1x1 plus R2x2, so on Rn xn. Okay. Suppose, how you prove this theorem? Suppose there is an ideal which is not finitely generated. Let S be the class of all ideals that are not finitely generated. Then definitely S is non-empty. Why? Because we have taken I is an ideal which is not finitely generated. So now we apply John's lemma to get a maximal member in S. Suppose U suppose U is any chain, capital U is any chain in S. Then you take I naught. I naught is union of the set of all I belongs to U. I told you union of any two ideals is again a ideal. So if this is finitely generated, there exists elements x1, x2, etc., xn belongs to I naught, which generate I naught. That is, for each xi belongs to ii, for some ii belongs to s, no one of these I1, I2, etc., in should contain all the ii. Why? Because you have U is a chain, and U is a chain means you have either I1 is contained in I2 or I2 is contained in I1. Only one will happen, not all. Okay. So S satisfies the hypothesis of John's lemma, and S has a maximal member which is prime. So you have, now we arrived at a prime ideal which is not finitely generated. So which contradicts to the hypothesis. Therefore, every ideal of R is finitely generated. Okay. So rings in which every ideal is finitely generated is called Noetherian ring. Okay, Noetherian ring, which will be, which we will study in the later chapters. Students, once again, see here, the above result only important. If P is any ideal, if P is not finitely generated, if P is not finitely generated and it is the maximal among all ideals that are not finitely generated, then P is a prime.
Prime.
Okay, then P is a prime ideal. By making use of this, what we will do, proof don't read them. Just go for, this is also for 5 marks.
Is it important, ma'am?
Yeah, important. This is important. If R is a ring in which every prime ideal is finitely generated, then every ideal of R is finitely generated. Yeah, right. Students, give one reading for this. You have any doubts means I will explain.
So there is an ideal which.
Okay. Next one, see here. All these, read it as results only. No need to learn all these theorems. Results in the form of results. You prepare a notes. I'm telling you, you make a habit of writing. 10 times reading is equal to 1 time writing. You prepare a notes. All these statements you prepare as results. If P1, P2, etc., Pn be prime ideals, and I is an ideal of ring R, such that I is a subset of P1 union P2, etc., Pn, then definitely I is contained in some of these ideals. Okay. And the next one is, see, if I1, I2, etc., In be ideals and B let and P is a prime ideal of a ring R, such that I1 intersection I2 intersection In is a subset of P, then II is a subset of P and D. This is also result only. Anywhere if you want means we will use.
Okay, ma'am.
Students, last class I discussed about integral domain. What is an integral domain? Integral domain is a commutative ring. A commutative ring with a unity that has no zero divisors. No zero divisors is called an integral domain. Okay, see here. When do you say that an element A divides B? When do you, why 7 divides 35?
7
First,
7
yeah.
is factor of 35, madam.
Yeah, that is the reason. So when do you say that A divides B? Then if there exists an integer Q belongs to Z such that B is equal to AQ. We say that A divides B if there exists Q belongs to Z such that B is equal to AQ or B is a multiple of A. Okay, and see here, if P is any prime, P is any prime, then P divides AB implies either P divides A or P divides B and D. P divides AB means P divides A or P divides B. So we call this integral domain an integral domain. D is called a unique factorization. Unique factorization domain, that is UFD, unique factorization domain, if every non-zero and non-unit element of D can be uniquely expressed as product of finite number of prime elements of D. Prime elements of D. What do you mean by a prime element? You have P divides AB implies either P, we say that an element P is prime. If P divides AB implies either P divides A or P divides B, then we say that it is a prime element. Okay, so an integral domain D is called a unique factorization domain if every non-zero and non-unit element of D can be uniquely written as a product of finite number of prime elements of D. Okay, Andy? Now see here. If D is any integral domain, suppose D is any integral domain and you have P not 0 not equal to P belongs to D. 0 not equal to P belongs to D. Then what do you mean by prime element? Then P is a prime element. Then P is a prime element if and only if principal ideal. If and only if the principal ideal is a prime ideal. Okay, then we say that it is a prime ideal. That is what we call it. Principal ideal is a prime ideal. What do you mean by principal ideal, Andy? What is a principal ideal? It contains all multiples of A. Okay, suppose if you take Z and Z తీసుకుంటే, see, 2. What is the ideal generated by 2? We'll take -4, -2, 0, 2, which contains all multiples of 2. It is a principal ideal generated by 2 only. Suppose if Z is generated by 5, all prime numbers if you take, Z is generated by 7. If you take ideal generated by 5, ideal generated by 7, these are all prime numbers. And in such case, only we say that P is a prime element. So whenever this is a principal ideal, this number 5, 7, these are called prime elements of the integral domain Z. Okay, Andy?
Okay, ma'am.
In this, you have one important theorem. Let D be an integral domain. This theorem is important for 10 marks, Andy.
Okay.
Till here, I have given only 2 marks questions, only 2 10 marks questions. Am I right? You from unit 1 and 2, you learned these 2 theorems, and 5 marks also I have given 3. That's all. They are only very important. With this theorem, I will stop today. See, let D be an integral domain. Am I teaching fast? Are you able to follow?
No. Yes, ma'am.
Yeah. Okay. Let D be an integral domain. Then D is a unique factorization domain if and only if every non-zero prime ideal contains prime element. Every non-zero prime ideal contains prime element. Suppose, see here, read the statement, read in between the lines, what he is saying, what we have to prove. Okay, he is saying that D is an integral domain.
Integral domain.
When this integral domain will become unique factorization domain, I told you just now. What is a unique factorization domain? Unique factorization domain lo em kavali manaki non-zero element.
Prime ideal.
Then you can write it as the product of prime elements. Okay, ma? So
Okay.
You have to write them as prime elements. Then only this integral domain will become unique factorization domain. So if and only if means you have to prove the theorem in 2 parts. First, suppose D is a unique factorization domain. Prove that every non-zero prime ideal contains a prime element. అంటే మనం ఏం చేసుకోవాలంటేనండి, ప్రైమ్ ఎలిమెంట్స్ అంటే మీరు ఏదో కన్ఫ్యూజ్ అవ్వద్దు. యాక్చువల్ గా సపోజ్ ఇఫ్ యూ టేక్ 105 అండి, 105 ఎలా రాసుకోవచ్చు? 3 into 5 into 7. Can you find any other representation of 105? No. So every integer greater than 1 can be expressed as product of primes uniquely. Every integer greater than 1 can be expressed as product of primes uniquely. So 105 means 3 into 5 into 7. Suppose if I take 12 and 12 can be written as 2 square into 4. You can write only powers. Suppose if you take n can be written as p1 power alpha 1 into p2 power alpha 2, etc. pn power alpha n. Okay. Now, coming to this theorem, suppose D is a unique factorization domain. Let P be any non-zero prime ideal. Since P not equal to D, every element of P is a non-unit. So since you have 0 not equal to P not equal to D, we can choose an element A such that A is equal to P1 into P2 into etc. Pn. Because D is a unique factorization domain. Because D is a unique factorization domain, every non-zero element can be expressed as a product of prime elements. That is A equal to P1 into P2 into etc. Pn. Okay. Now you have A equal to P1 into P2 into etc. Pn belongs to P, and P is a prime ideal. Okay, and it is P is a prime ideal. You have some Pi belongs to P. Your Pi is a prime ideal. This prime element is in P. Okay, this is what you have to prove. And the next one, conversely, suppose every non-zero prime ideal D contains a prime element. Ikkada, since P is prime, kabatti you have Pi belongs to P and raskondi ante. Either any edo okati untundi indulo. Conversely, suppose every non-zero prime ideal D contains a prime element. Let T be the set of all products of finite number of prime elements in D. Then what we have to prove here, conversely, suppose every non-zero prime ideal D contains a prime element. What you have to prove? Any element in D can be expressed as product of these prime elements. For this, you have to take some prime elements, no? For that, you take, let T be the set of all products of finite number of prime elements in D. So we prove that T is saturated multiplicatively closed set in D. What do you mean by anta confuse avakandi meeru? Saturated multiplicatively adanta rayakapoyina parvaledu. What you have to do? You have to, if P1, P2, P3, P4, etc. These are all prime elements. Any A can be written as P1 into P2 into etc. Pn. Okay. So you have, we can write AB is equal to P1 into P2 into etc. Pn, where each Pi is a prime element. Now, P1 being a prime number, okay, and if P1 being prime, we should divide either either A or B. See here. You have taken AB is equal to P1 into P2 into etc. Pn. You take this as one element and Q anukondi. You have AB equal to P1Q.
P1.
What do you mean by this? P1 divides AB.
AB.
P1 divides AB means P1 divides A or P1 divides B. What do you mean by P1 divides A? What do you mean by P1 divides A? There exists some A1 such that A is equal to P1 A1. Am I right?
Yes, ma'am.
So PA is P1 A1. Tell me what is AB? AB is A into B.
A.
Is P1 into P2 into etc. Pn. So since D is an integral domain, it follows that you have A1B. Integral domain and cancellation loss andi. Okay, zero divisors undavu kada.
Yes.
Ikkada nenu vivaranga rasta undandi 1 minute. Ikkada konni points rastanu. Oka 5 minutes lo ayipotundandi theorem.
Okay, ma'am. Okay.
I won't take much time. With this theorem, we will stop. See here. We have to prove D is unique factorization domain. Okay. So we will write AB is equal to P1 into P2 into etc. Pn. This belongs to T and D. T is multiplicatively closed set. So you take this AB is equal to P1 into Q and where Q is P2 into P3 into etc. Pn. This implies P1 divides AB. What
AB.
is P1? P1 is prime. P1 is prime means you have either P1 divides A or P1 divides B. So if P1 divides A, then there exists some A1 such that A is equal to P1 A1. So what is AB amma manaki? AB you have P1 into P2 into etc. Pn.
Pn.
So you have P1 A1 B is equal to P1 into P2
P1 into P2 into and so on Pn.
Pn. Okay, Nana? Now you have P1 into A1B minus P2 and so on. Pn is 0. Since P1 not equal to 0, you will get A1B minus
A1B minus
P2
P2,
into
P3
P3
and so
into
on
etc.
Pn equals
Pn
to
is
0.
0. Or you will get A1B is equal to P2 into P3 into etc. Pn. Or you can have cancellation loss holds and good pettukochama. I told you, no, or a ring has 0 divisors if and only if it satisfies cancellation
loss.
Yeah. So now we'll see. We make use of induction on N to prove that either A1 or B is in T, and here we will prove either A1 or B is in T. So that A or B is in T. So that you will get T is saturated multiplicatively closed set. And we have proved that R minus P, guttunamma, R minus T is union of prime ideals of D and cheppunnam akkada. Now, let A be any non-zero and non-unit element in D. If A does not belongs to T, if A does not belongs to T, implies A belongs to T complement. What is T complement? R minus T. T complement is R minus T. So there exists a prime ideal P such that A belongs to P, which is a subset of R minus T. So by hypothesis, this prime ideal should contain a prime element P, which will not be in T. So this is a contradiction. So thus A belongs to T. That means every non-zero and non-unit element in D can be written as a product of finite number of prime elements. Okay, Andy? So this is the theorem. Hence, whenever D is an integral domain, it will become a unique factorization domain if and only for every integral domain.
Non-zero prime ideal contains a prime element.
Every integral domain can become a unique factorization domain if every non-zero prime ideal contains a prime element. Okay, Andy? Is it clear?
Yes, ma'am.
Here you can write it. Okay?
Okay, ma'am.
So in this, others no need to study other theorems. Ivanni entante, see next one, let I be a proper ideal of a ring R, then ivanni isomorphism lo cheddam. We'll do in isomorphism.
Okay, ma'am.
Yeah. In the next class, Emma, with this, we will stop by unit 1 and unit 2. For the next class, come prepared with unit 1 and unit 2. You have any doubts in the theorems means you ask me. I will clarify your doubts. Okay?
Okay, ma'am.
Okay, madam.
Yeah. In this, only 2 10 marks questions and 5 marks questions too you read. Because coming chapters, no, they are very easy. These are only important concepts. Okay?
Okay, ma'am.
Important in the sense we are going to use these concepts in the next coming units. Okay.
Okay.
Okay. See you on Saturday, next Saturday.
Okay, ma'am. Thank you, ma'am.
Now.
Thank you, ma'am.
Okay, you are welcome.